All right, today we're going to get our hands dirty. Well, figuratively anyway, and dive into the actual rule book for building the internet. We are going deep inside the master plan for the glass veins that carry our entire digital world.
You know, it's a question we almost never think about, right? We just expect the internet to be there, to just work. But behind every single flawless video call, behind every search result that pops up in a split second, there's this massive physical construction project. And it's all governed by an unbelievably precise set of rules. This technical standard, this is the answer.
So, here's how we're going to tackle this. We're going to follow the life of a single fiber optic cable through 4 main stages. First up, we'll look at the master blueprint, where every single millimeter is planned out. Then, we'll see how that drawing becomes a real-world path. After that, we'll zoom way in on the microscopic surgery of connecting these tiny glass strands. And finally, we'll cover the final inspection, the test that gives the whole thing the green light.
So our journey starts, maybe surprisingly, not with a shovel, but with a huge stack of documents. Before a single inch of ground is ever disturbed, this intensely detailed plan has to be created, mapping out the entire life of the cable from start to finish. Now, the whole point of all this crazy planning is to fight against a fundamental law of physics, something called attenuation. It's actually pretty simple. As light, which is our data, travels down that glass fiber, the signal gets weaker and weaker. So the entire goal of this master plan is to design a system that minimizes this signal loss as much as humanly possible.
And when I say detailed, I mean obsessive. The sheer amount of stuff that has to be documented is just incredible. We're talking about the cable's specific brand and model, the exact GPS coordinates of every single splice, precise measurements between manhole walls, and even a map of every other utility line, gas pipes, water mains, that crosses its path. Absolutely nothing is left to chance.
Okay, so the blueprint is approved and locked in. Now the plans get handed over to the field crews. The new challenge is turning those perfect drawings into a physical reality, getting miles and miles of this delicate cable safely into the ground. And there are basically 3 ways to do it. The most common methods are pulling it through existing underground pipes, which are called conduits, or just burying it directly in the earth. That third method, stringing it up on poles like old-school telephone lines, well, that's the most restricted. You actually need special written permission from way up the chain to do that.
Now think about pulling something this delicate for miles. The rulebook is incredibly specific about the forces involved. The absolute maximum pulling tension allowed on a standard fiber optic cable is 600 pounds. That is, unless the manufacturer explicitly says you can go higher, and they have to use a tension monitoring device that someone watches constantly during the entire pull to make sure that limit is never ever broken. This is probably my favorite detail, because it just shows you the level of care we're talking about. The bending radius is how sharply you can bend the cable before you risk cracking those tiny glass fibers inside. When the cable is just sitting there, not under any tension, you can bend it in a curve that's 10 times its own diameter. But the second you start pulling it, that rule doubles. You need a much wider, gentler curve, 20 times the diameter, to keep it safe.
And if a cable is buried without any extra protection like a steel conduit, it has to be deep. The standard demands a minimum depth of 1,200 millimeters. That's almost 4 feet down, all just to protect it from being accidentally dug up by some future construction project. But, just in case, there's a brilliantly simple, super low-tech backup plan. A bright orange warning tape is buried in the same trench, but only about a foot below the surface. So if someone starts digging years from now, the idea is they'll hit this plastic tape long before their shovel gets anywhere near that critical fiber optic cable buried deeper below. All right, the cable is in the ground, but it's not one continuous piece. It's in sections. So now comes the most delicate, most precise part of the whole process, splicing. This is basically microscopic surgery, where technicians join individual strands of glass, and each one is thinner than a human hair. The rules here are just incredibly strict, not just for precision, but for safety. I love this quote from the standard, because it shows that even where you're allowed to do the splice is regulated. Fusion splicing involves creating a tiny electric arc, so it has to be done out in the open air, well away from any potentially dangerous gases that could have collected inside a manhole. So you've got 2 main ways to connect the fibers. A fusion splice literally melts the 2 glass ends together so they become one continuous piece. A mechanical splice, on the other hand, just aligns them perfectly and uses a tiny clamp to hold them in place. But look at these numbers.
The maximum signal loss you're allowed to have from a fusion splice is just 1/10 of a decibel. The level of precision is just staggering.
Now, here's a detail that really just brings the human element into all of this. Those tiny little scraps of leftover fiber, they're like microscopic glass needles. They are so sharp they can easily get into your skin and you'd never even feel it. The standard actually tells technicians they have to clean them up by dabbing the area with the sticky side of tape to make sure no dangerous little slivers are left behind.
And this is the most important warning in the entire document, hands down. The light traveling through these fibers is a laser, but it's often in the infrared spectrum. That means it's completely invisible to the human eye. If you look into a live fiber, you could suffer serious, permanent eye damage, and you would never even see a flash.
So, the cable is laid, the strands are all spliced, everything is connected. But the job is not done. Not even close. Now comes the final exam. A whole series of tough tests to prove that the installation meets the master plan's incredibly high standards. There are 3 acceptance tests that are absolutely non-negotiable. First, they test the cable while it's still on the giant reel, before it's even installed, just to make sure it wasn't damaged on the way to the site. Then, they test every single splice, one by one, right after it's made, to make sure it's a good connection. And finally, when it's all put together, they do the big one, the end-to-end test, measuring the total signal loss across the entire length of the cable. And that final test, it's graded against something called the link loss budget. This is a number that was calculated way back in the design phase. It's the absolute maximum amount of signal that can be lost for the system to still work correctly. If that final measurement from the field is even a tiny fraction higher than this budget, the entire link fails. It's a simple pass-fail grade for the whole multi-million-dollar project.
And that really brings us to the final thought here. After seeing the insane level of precision required at every single step, from the blueprint to the final test, it makes you realize that our seamless, connected world isn't magic. It's actually this massive, surprisingly fragile system that's built on the flawless execution of thousands and thousands of these tiny, critical rules. And a single mistake, one broken rule, could be the difference between a perfect connection and a totally dead link.